Alright, so we got our hot dogs cooking. We're relying here on our good old propane tank to power this grill, keep the fire going. And the propane tank is just awesome, right? It's a pressure vessel. We see it's a cylindrical pressure vessel because it has some portion, a flat portion here along the length, so it's got two caps and the flat portion here, so that definitely makes this a cylindrical pressure vessel. You could see that these calculations that we would want to know might be important for maybe this weld seam here that's in the middle of our pressure vessel. Of course, we have our valves to release some of that pressure if it gets too high inside, and it's just an amazing thing, right? The pressure vessel. It's a thing. Oh my goodness, I've left the hot dogs on too long. You gotta check them. I hope they're not messed up. What happened to them? Oh, they split. Wait a second. Are hot dogs a pressure vessel? I think they could be. Why do they always split along the length here? Oh, perhaps maybe the stress in the circumferential direction or the hoop direction, perhaps that stress is higher than the longitudinal direction. We never see hot dogs busted out the end. Anyone who's ever cooked a hot dog too long, as I'm sure you have, knows that it always splits along the length. So perhaps we already intuitively know that the hoop stress is going to be a little bit higher than the longitudinal stress. As I like to say, when in doubt, look to the hot dog for inspiration, right? So now that we've seen our model, our physical model, we know that the hoop stress is always going to be higher than the longitudinal stress in a cylindrical pressure vessel, because the hoop stress is what causes a hot dog to split along its length when we overcook it. So go ahead and jot that down in your notes however you wish to remember it, so that you can always, next time you're at a party or an outdoor barbecue, you can bring up pressure vessels, explain it to your mom and dad or your friends. They'll all love you for it, and they'll be like, wow, we're so interested in engineering. We really need to tell us more. We want to know so much. Tell us about all the problems you did in mechanics and materials. It's so interesting. Well, I like to dream, at least. Alright, on to the derivation for cylindrical pressure vessels. Let's go ahead and first look at the longitudinal stress. So to do this, I want to take a section at point A. So you see point A in there. I want to pass a vertical plane into the page through point A. So let's go ahead and try to sketch this into place. So imagine this green plane crossing through the pressure vessel. If I pass that section through, the black section is sort of the cross section through which I'm cutting through point A. And I've sketched that cross section to the right. So we can see that the circular cross section on the right is what I'm sketching from this section. So like everything we do in mechanics and materials, we like to draw free body diagrams, and so this derivation is going to be no different. So I have now my section cut, which is basically a free body diagram, and now I'm going to perform equilibrium on the section. So the shaded gray area there is subject to an internal air pressure in this particular canister. So the pressure inside the cylinder is acting over this shaded area in gray. So I'll go ahead and put a bunch of little black arrows there, and I'll label them. This is the pressure, lowercase p, that acts over the shaded area. Now, like we do in statics, we don't really want to work with the pressure because we can't use pressure or stress in an equilibrium equation. So I want to convert my pressure into an equivalent or a resultant force acting on that shaded section. So that resultant force I'm going to draw in as P2, and this will be the resultant force from the pressure acting over this shaded area. To be in equilibrium, P2 has to be balanced by another force, and that is going to be the stress in the material that's resisting the load applied. So I've shaded in the material, the circular section, the circular cross-section of material that's resisting my force P2. That circular cross-section is going to be subject to some sort of stress, sigma 2. And so I want to write an expression for what sigma 2 is. Sigma 2 is balancing the force P2 over a distributed area of A2. So this is just our normal stress equation that we learned basically on day 2 of class. Sigma 2 equals force over area, or P2 over A2. So now I need to come up with expressions for what P2 and A2 are. P2 is the pressure acting over an area. That area will be pi r squared. So I multiply my pressure times an area, pi r squared, where r is the inner radius of this pressure vessel. So that gives me an expression for P2, so that is now a force. And that force is being distributed over A2. Now I could calculate A2 by doing pi r squared of like the outer radius minus pi r squared of the inner radius. But remember, we're using what we call a thin-walled approximation. And it's easier if we just assume that the outer radius and inner radius don't change much. And so we can get the area A2 by basically taking the circumference, which is 2 pi r, and multiplying it by the thickness of the material T. If we do this, we can go ahead and cancel some things out. Pi will cancel, and one of the r's will cancel on top. So this will leave us an expression for sigma 2. Sigma 2 is equal to PR over 2T. So there we have it, with just a little bit of free body diagrams and some statics. We've gone ahead and we've come up with an expression for the longitudinal stress, or the axial stress, in a cylindrical pressure vessel. We're now going to follow the same procedure to come up with an expression for the hoop stress, or the circumferential stress, in the cylinder. So again, I want to pass a plane through the cylinder, so I think it's easiest to visualize this as a horizontal plane cutting through the length of the cylinder. And so when I do that at point A, I'll be left with sort of a half hemispherical like section or shell of a shape. So I'll go ahead and try to draw that in black here, so you can imagine that as I pass this plane through the middle of the cylinder, I end up with this sort of circular section here at point A. And I'm going to take just a strip. I'm going to take a finite strip of this cross section. Alright, so I've taken that strip and I've kind of flipped it on its side and sketched my free body diagram to the right. So just like before, on this free body diagram, we have the pressure inside the cylinder acting. So we can represent that pressure with a bunch of little black arrows that is acting over the shaded area in gray. So again, I'll go ahead and label that small pressure P. Alright, to do my force balance, I'm going to need to come up with an expression or a resultant force from this pressure. So I need a resultant force, P1, that'll be applied through the center of gravity of the shaded area. So I'll mark out the center of gravity, and I'll show my resultant force, capital P1. As capital P1 presses against that shaded area, it tries to push that half circle piece away from the other half circle, and that's what's causing the stretch in the hoop direction. Now what's resisting the expansion is the material, the thin material in the wall of the cylinder. So I've shaded the area of that material in blue. So we see we have a little chunk of area on the top and a chunk of area on the bottom. Just like before, we'll come up with an expression for sigma 1, and it's going to equal P1 over A1. P1, my resultant force, will be my pressure over the area over which the pressure acts. That area is going to be a total height, that rectangle height is going to be 2 times my radius. So I see one dimension of that shaded rectangle is 2 times r. And then the width is going to be, well, however big of a chunk of section we took. So I'm just going to call this any old width dx. So just say this is a small little segment dx. And I'll go ahead and label dx on both my free body diagram and my original picture where I made the cut. So 2r times dx gives me the shaded area in gray. Now I need to come up with an expression for a1. a1 is just going to be that width dx times the thickness of my material. So it's just going to be t times dx. And then I have a chunk of material on the bottom of that hemisphere and a chunk of material on the top. So I multiply t times dx times 2 because I have 2 cross-sectional areas resisting that force. Go ahead and cancel out 2 and dx from the top and bottom, and we're left with an expression that sigma 1 equals PR over T. So hopefully you managed to stay awake during this derivation and it wasn't too burdensome. It was a good use of statics and some of our mechanics and materials to come up with some quick formulas for our pressure vessels. I just want to point out that as we expected, our hoop stress is larger than our longitudinal stress. So we look to the hot dog for inspiration and we see that the hoop stress is indeed larger than the longitudinal stress. In fact, the hoop stress in a cylindrical pressure vessel is always twice the value of the longitudinal stress. And so that is why hot dogs always split along their length, or any kind of cylindrical pressure vessel will always split along the length because the hoop stress is always larger. Finally, I want to consider spherical pressure vessels. So being that we're living here in West Texas, we see a lot of spherical vessels in the application of, especially in the oil and gas industry. So a lot of the oil and gas pressure vessels on industrial sites tend to be spherical, or even the vessels that transport them from one place to another are spherical. We can do another derivation for a spherical pressure vessel, but no matter which way we pass the plane through a spherical pressure vessel, we always get the free body diagram at the top of this page in notes. Namely, we always get that circular cut, that circle free body diagram. So therefore, our stress is always going to be PR over 2T. Whether we're looking in one direction or the other, it's always stretching. So for a spherical pressure vessel, we see that the hoop stress and longitudinal stress are always the same. I hope everything we did here made sense. Let's look at another application of cylindrical pressure vessels. So now we know how to calculate the hoop stress and the longitudinal stress in both cylindrical and spherical pressure vessels. So I wanted to take a first-hand look at a cylindrical pressure vessel. So a basic cylindrical pressure vessel looks just like the soda can that you probably encounter every day in your life. Maybe that favorite energy drink of yours that you're drinking to make sure you can stay up and do all these notes and get all the homework done, right? In our lab, we're actually going to strain gauge the soda can to measure the pressure that they use in packaging the soda for distribution. Now, when we do that, we know that the hoop stress is going to be higher than the longitudinal stress. And as part of the strain gauge process, we need to sand down the surface to make sure that we get a good adherence for a good surface to have our strain gauge adhere to the soda can. Now you want to be careful when you're sanding, because if you sand too much, you'll actually sand through the material. And sometimes it just creates a little nick and then soda starts squirting everywhere. But other times I can be more explosive than that. So we know pressure vessels tend to having drastic failures. And so actually when a student last semester was doing this experiment, he sanded too far and you see it ripped open suddenly on him. And in fact, it ripped in this direction along the length because the hoop stress is always higher than the longitudinal stress. So no surprises there at that fracture. All right, so I'm looking forward to doing this with you in the lab, and I hope you're enjoying our day on pressure vessels.